So we're going to begin rational functions in general. So when we talked in the beginning of the year, we talked about rational versus irrational versus imaginary. We have different types of numbers. So to reiterate, who remembers what is the difference between? And now again, don't confuse imaginary. But what is the difference between rational and irrational? This was like concept 1, I think, actually, of the whole year.
Yeah, real numbers and not
That's imaginary. You're confusing that difference. That's what we're talking about. Leslie, Barbosa? Yes, rational versus irrational. Those are types of rational numbers. Kelly?
Irrationals are not perfect squares and they're under the radicals.
Irrational, a good example was something like square root of 3 or square root of 7. Those were irrational. Very good. That's one example of irrational.
Rationals are predictable, irrationals aren't?
Absolutely. Very good. That's the way we thought about it. And you all from memory, right?
Yeah.
Very good. Rational was thought of as if they have a decimal in there, it's going to be predictable. So for example, rational were examples like 1/2, because 1/2 is just 0.5. The decimals are predictable. It's 0.5. That's it. But remember we talked about something like pi. Pi is 3.141526, and it goes on and on forever with no pattern. That was irrational. Okay, so today, and for the next about 9 or so concepts, we're going to be studying rational expressions. So things that could be written as fractions. Any repeating decimal, any terminating decimal could be written as a fraction. For example, who knows, as a fraction, what is 0.33333333333 forever? It's 1/3. It's 1/3. It can be written as a fraction. But something as simple as 0.25. What's 0.25 as a fraction?
1/4.
1/4. 1/4. Because 0.25 is like a quarter, right? A quarter in your hand is 25 cents. Okay, so 0.25 is like a quarter, or 1/4. So whenever we do these concepts, when we're looking at rational things, we're going to be looking at things that are written as a fraction. Okay? So again, today we're going to look at simplifying these. So we're going to think about rational expressions as fractions. Now, for the first thing we say here is this. In order to simplify or to cancel things out, you must have factors. So, what is a factor? What is a factor? You can tell me what a factor is.
A number, it could be multiplied by.
I know what you mean, but your definition is not stated correctly.
Okay, a number that you use to multiply to get. Okay, no,
Kelly, you're absolutely on the right track, but you're not defining it correctly. Somebody give her a little help. What would a factor be defined as? No? Let's go to an example. Tell me what the factors are of 36, starting with the smallest.
2, 4.
Well, you missed the smaller one.
1.
Good. 1 and
36.
2 and
4.
14.
Try and do them in pairs. 18.
Oh, 18, okay.
3 times what gives you 36?
12.
4 times?
9.
6 times? 6. Be careful. 36. So, aren't these all factors of 36?
Yeah.
So, based on that, what can you tell me is a definition of a factor?
Numbers that make
Numbers that go into
Andy?
numbers that go into
Yeah, it's pretty much numbers that can be divided into the original number. That's what a factor really is. It can be broken up this way. So I heard like numbers that when put together give you this number. Yes, that's the right idea, but you want to say something like 2 numbers such that their product is the original number. 2 times 18, product, is the original number, okay? So if we're going to think about factors, we want to think about factors as like the foundation of our number. So a number like 6 is made up of 1, 6, 3, and 2, really, right?
Yeah.
Those are the whole number of factors that go into it. Today we're going to be doing a lot of factoring, whether it's greatest common factor or whether we're factoring quadratic into like x plus 2, x minus 3. We're going to be factoring over and over again, okay? Now, the only way you can simplify an expression is if the numerator and denominator have the same factor. Here is a common mistake given. Take a look here. The person decides, okay, there's x over x plus 2, and they say, well, we can cancel those x's, and then you're left with just 1/2. That's not true, though. Who can tell me why this isn't true? Looking at this original statement right here, and based on what we just said, why can you not cancel the x's?
You don't know what it is.
One at a time.
Don't
Manuel?
Isn't it X1?
We don't know what x is. We're just saying variably. Ignore this for now. Just looking at that. Why can't I cancel the x's? Is the question. Why can't I cancel that?
Because it must be the same factor in the numerator and the denominator.
Okay, well, I see an x in the numerator and denominator, Kelly.
But we don't know what x is.
Has nothing to do with that. You were closer in your first
You
statement
said,
than you
why
were in the second.
can you or why can't you?
She said, you have to have the same factor in the top and the bottom. I said, well, there's an x in the top and the bottom, so why can't I just cancel? And then her response was not correct for the second part. So my question is, why can't I cancel the x's?
Because the bottom one is it's a whole thing.
It's being added.
It's not just an x, it's like a whole thing. So it's a binomial.
It's a binomial. Very good. The denominator is a binomial. Now, this x here and this 2 here, they're not being multiplied. If they were being multiplied, then you would think of them as factors. So if you had x over 2x, then the x's just cancel, and you get 1/2, because a 1 remains behind here. Because these are factors, because they're being multiplied here. But here, guys, focus, come on. Here, they're not being multiplied. What are they being done? Added. What do we call two numbers that are being added together? Not factors. There's another word for it.
Add-ins.
What are they?
Add-ins.
Add-ins. Very good vocabulary, Kelly. Only person in all 3 classes to get that today. Nobody in first or third period got that one. Very good. X and 2 in this case, in the denominator, are both add-ins. A-D-D-E-N-D. That's how you spell add-end. It's one word. Okay, one word. So again, the x and the 2, since they're being added together, are considered to be add-ins. So in this case, I cannot cancel the x's. Well, what about this? What if I had 2x over 2x minus 7? A lot of people are tempted to cancel the 2x's. But these are not being multiplied in the bottom. See how the 2x and the 7 are not multipliers anymore? They're being subtracted. So if they're subtracted, what is the definition of subtraction? Negative. The negative or the opposite. Very good. So, really what I have going on here is this. You need to think of this as the following. Isn't that what's really going on here? Instead of subtracting 7, you're adding negative 7? So aren't these then add-ins automatically? Okay, these are both add-ins still. So again, I cannot cancel the 2 x's there. I can only cancel if I have multiplication on the top and the bottom. Okay, again, if this was multiplication instead of addition here, then you could have canceled the 2 x's. So let's take a look at our first example from this. Okay, let's think for a second to ourselves. What gives us the ability to simplify a fraction? So think about a fraction that can be simplified. Give me an example, somebody. What is it? 3/6. Juan, you're thinking the same thing? And everybody says they're both divisible by what? 3. Okay, good. Now, where did you actually learn this? Here's how you learn it, actually. You write it this way. That's really what's going on there, isn't it? The numerator is really 3 times 1. The denominator is really 3 times 2. That's where the 3 and the 6 come from. Then what happens to my 3's? What's left behind when they cancel? A 1. Well, a half is there, but in their spots, sorry. In their spots are just 1's left behind. Again, and then you see, well, 1 over 1 is just simply 1, so this becomes 1 times 1/2, which is really still just 1/2. So where does simplification come from? It comes from factoring, really. You're factoring this into its common factors, and then you're canceling those factors. Okay, I know this sounds very simple, and it looks like, oh, why are we doing this? In a minute, we're going to start looking at variables, and it gets a little bit more complex with that. Okay, again, here, we break this into 3 by 1 and 3 by 2. 3 is reduced to 1 over 1. But what's 1 over 1? It's just 1. And then 1 times a half is just a half. Okay, this works for anything. What about 9 over... Nah, it's going to be a factor of 3 again. Let's try a different one. Let's try 8 over
64.
28. 8 over 28. What can they both be reduced by factors of?
4.
4. Very good. So think of it in your mind as this is really 4 times 2. This is really 4 times 7. Right? What happens to the 4s?
Cancel.
What are you left with? 1 times
Oh, we're not supposed to.
2 over 7. Very good. Again, when you cancel the 4s, you got 1s left behind. And then they multiply by 2 7ths. Again, every single time you do this, this is what you're really doing in your mind. And I know some of you can do it quicker, and that's good. You don't have to show these steps. But in a minute, when we get to variables, it is good to show the steps along the way. You're going to probably need to do it, actually. Okay? Are we clear?
Yeah.
All right, so this is an example of factoring. Now, before we go on to the next slide, we need to talk about something that we call the GCF. Greatest common factor. Okay? If I had that binomial on the board, can somebody tell me how to factor out the GCF here?
It's 2.
It's 2 because they're both even. You see that right away. Now, Kelly, what's left?
Excellent.
Karen.
Oh, that was Karen? Sorry.
Oh,
X plus 4.
yeah.
Now, where does the X plus 4 come from? Who can explain this? And think before you answer, please. So it's a harder question than it seems. Some of you just know that it's X plus 4, but where does it really come from? Very good, Kelly. Very good. And she remembers. See this 2 here? And I showed you guys this in the beginning of the year real quick. Whatever you factor out as the GCF, whatever comes out here, divide everything by that. And then look at what's left over if you did that in your head. 2x over 2 would just be x. These 2's would really cancel. 8 over 2 is really 4. Again, whatever comes out as a GCF, divide each term by that GCF in your mind. You don't have to show it on paper. Okay, if you can get right to the answer, that's fine. Now, another way to check. What's another way to check that you got the right answer here? Good. Multiply it back out or distribute it. This becomes 2x. This becomes 8. 2x plus 8. That is correct. Okay? That's an easy example. Let's do one like this. What if I have... What about this one?
3.
3, right?
Oh, 3x. 3x.
3x squared.
Oh, 3x squared.
Notice, you can take a 3 out of the numbers, so you start with the numbers. 3 and 18 are both divisible by 3. That's good. Then we go on and say, what can go into x squared and x cubed? Well, x squared is in both of them. If I think about this, if I take a 3x squared out of 3x squared, what's left?
6. Nothing.
Again, if I take a 3x squared out of 3x squared,
Oh, nothing.
1.
Oh, 1.
Remember, it's like you're dividing. It's like you're dividing by 3x squared, and you're dividing by 3x squared. What happens here? They cancel, yes, but you're left with a 1. It is extremely important that you remember. Everything okay? That you remember.
Laughing at my thoughts.
It is very important that you remember here. If you cancel something out, there is a 1 left behind, because this one placeholder is a big deal here. Now, 18 divided by 3 is?
6.
6. And I have 3 x's here, or x cubed, and 2 of them here. So I'm left with 1 of my x's up top. Again, there was x to the third over x to the second. So 3 of these x's, 2 of them cancel with 2 of these, and I'm left with 1 of them up top. That 18 and that 3 reduces to 6 and 1. So this is what you get when you factor out the 3x. Okay, we're going to use these skills today. Can we focus? Whatever it is, just, you know. Now, you don't have to write all this down. Okay? Let's start by talking first. It looks like a complicated thing because there's a lot of words here. I want to talk to you about electric field. So, an electric field is something where you have 2 different charges. So you might have like a metal plate here and a metal plate here, with all negative charges and with all positive charges. This is really called a capacitor. Now, when you have an imbalance of charges, you get a field between them. So in physics, we define the electric field as the force per unit positive charge. And simply, as an equation, this is what it means. So I want you to start by writing the equation out, please. So E of t equals F of t over Q. You don't have to memorize this again, guys, just like you didn't have to memorize last chapter. We did stuff with momentum, with tangential velocity, we talked about torque. Okay, all that kind of stuff. You don't have to memorize all of that. It's going to be given in the problem. So we start by looking at our formula. We told that the electric field intensity is the force over the charge. Okay? So it says determine the electric field intensity. So figure out what E is equal to. Okay, the function E. Now, I'm given F of T and I'm given Q. So we start by just writing it. So the electric field, based on our formula, is equal to F of T, which is 2T plus 4, over the charge, which is 8. Again, there's my charge, there's my electric field. Those both go into the formula. F of T goes in the numerator, Q of T goes in the denominator. And now at this point, what do you notice? What can cancel out of equation? What is it? What's in every term here?
2.
A 2 is in everything, right? Again, everything is divisible by 2. Now, let's show that, though. Let's show that. The numerator becomes 2 as an outside factor, as a GCF. What's left behind?
1 and plus 2.
1t plus 2. Good. Remember, you have a t there. Don't forget that you said 1, okay?
All right.
Again, how do I know this? I take my numerator and just divide it in my head by the GCF. 2t over 2 is just t. 4 over 2 is just 2 there. Now, what is 8 really? 4 times?
2.
4 times 2. So I want you to think of it this way now. And now take a look. I can cancel these 2's simply because everything is multiplication now. Notice, isn't there really a time symbol right there? In between the 2 and the t plus 2, there's a time symbol. So since these are factors in the numerator, and these are factors in the denominator, I can cancel the 2's. So I'm left with simply t plus 2 over 4. Again, I'm left with whatever's there. There's a 1 here, and there's a 1 there, but those have no effect on the problem. So again, I'm simply left with t plus 2 all over 4.
Does that just make it easier? Could you could plug in T and then just do the whole thing?
But this is not a problem that gives you t, though, Melissa. This is a problem that says simplify the rational expression. Okay? Again, you're right. If you were given a value of t,
Yeah.
it does help to simplify and then plug in t. It actually does. It makes it easier in a lot of cases. So it is good to simplify, especially on the next 2 examples you'll see. I'll show you. I'll bring it back up for that one. Now, here's what I also want you to notice. You could actually go further. You could try and divide the 4 into both terms here. See how the bottom is a monomial, 4, and the top is a binomial, t plus 2. You could divide this into both. And really, please, you don't have to write this, but I want you to understand, because on the SAT it could be displayed this way. You can write this as t over 4 plus 1/2. Again, if I were to simply take the 4 and divide it into both of these, which is completely fine or mathematically sound, I can divide the 4 into t over 4. 2 divided by 4 reduces to 1/2. So this is an alternate way to look at the answer. So keep that in mind. If you were doing a multiple choice in the SAT and you didn't see this answer, but you saw this answer, or you might have seen like 0.25t plus 0.5. Again, 0.25 coming from the fact that it's 1/4 really. This is really 1t over 4. That would be like 0.25 right there, and this would be like a 0.5. So you can see it that way also. But there are many interpretations of the same thing. So when you get an answer, just because your answer isn't there doesn't mean it's wrong necessarily. It might mean that it's not simplified to the way that the SAT wants it. And it depends on the type of problem. Some of the problems, they'll leave it like this. Sometimes they'll simplify further. So you have to look at the answer choices and see which of those choices is a simplification of my answer. Again, this might be my answer over here, but this might be the simplification that is shown on the SAT. Okay? So keep that in mind when you're performing these. Let's take a look at another problem. Here. Before we start this problem, please write down in your mind or on the paper. First start with the GCF. Okay, start with the GCF. Then factor the remaining. Okay, those are just going to be the only 2 steps that we're going to have here. The last step is to simplify or cancel, but that's the whole operation. So looking at this problem, right away you can't do much with the numerator. The numerator is just one monomial there, 4x squared. But the denominator is a binomial. So there's a good chance I can factor something out of the denominator.
3.
It looks like a 3 can come out of the 6, but can a 3 come out of the 20?
Yeah.
No, the 3 can't, so it's going to be a 2.
No.
Again, It looks like it's 3 because this can be divided by 3, but this cannot be divided by 3. That doesn't work. Okay, so we can't use 3 there. So we'll factor out a 2. That's a good idea. So what else is there, guys?
2x.
2x. Very good. How come there's an x there, Karen?
Because there's an x.
Is x in?
6x squared
And the 20x. Very good. Notice, there's a single x here in the 20, and there's x squared in the 6x squared. So you could take an x out of both of them at least, right? Because there's enough for one of each. Now, if I divide this by 2x,
3x.
and divide this by 2x,
3x.
you get 3x, very good, because 6 over 2 is 3. X squared cancels with the x. You're left with simply, again, the 3 and the x. This becomes what?
Minus
Very good. That's a 10. The x is canceled. Carry down the minus sign. And please, you can always check, and you always should do a mental check. Go ahead and look in your mind. 2x, 3x, do in your head. That's 6. There's 2 x's. That's x squared. Up 6x squared. 2x times 10 gives me 20x, and I carry down the negative sign. Now, since I factored the denominator like that, there might be a better way to rewrite the numerator so I can see what cancels. How can I rewrite the numerator now? Look at the numerator as it is right now. It's 4x squared, right?
Yeah.
What can I break that into?
4x.
2x.
2x, and what else? And 2x. Andy, why did you choose 2x? Because you could have done 4x times x. Right? I could break this up and do 4x times x. That still works, doesn't it? Why did you choose 2?
Oh, so the 2x down there get crossed out.
There it is. Take a look. Cancel, cancel. Why can I cancel?
Because
You
they're
remember?
multiplying.
Because they're all multiplying. Again, there's a multiplication symbol there. Don't forget that multiplication symbol in your head. It's not going to be displayed on the paper, but there really is a time symbol there between the 2x and that parentheses. So what's left over? 2x?
3x minus 10.
Very good. Now, a lot of people want to cancel those x's. Why can't I cancel the x's now?
Coefficient.
Okay, Josue is correct because of subtraction. It is not because of the coefficient. If this coefficient had been a 3 up top and you had a 3x, you still can't cancel. Again, you can't cancel because these are addends. Remember, even though there's subtraction, they're addends because you add the opposite.
In both
Okay.
multiplications, if you multiply, then you can do it, right?
Just like here. Since these were multipliers and these were multipliers, we were able to cancel the 2x's.
All right.
Okay? That's your common rule, guys. Common rule the whole way. Let's take a look at the next one. Please write it down. Fine.
I wonder what happened if I can. Chill.
Can I get a reader for this? Listen.
If h of x equals x squared plus 7x plus 12, and g of x equals x squared plus 2x equals 3, and k equals h over g, then determine the function of
So you can tell me what I should do here.
Factor those out first.
Okay. I would eventually factor them, yes. But what's my starting point? What am I trying to find?
You're gonna put h over. You're gonna put the equation of h of x over the equation of g.
Very good. Again,
Good job, Tyler.
k is defined as h over g. Since k is, it's a complement. If k is defined as h over g, we start by listing the h function. Again, this is h right here over g. There's the g function right there. Now what? Good. Is there any greatest common factor in either of them?
No.
No, there's not. Notice, the top and the bottom, there's no GCF for either of them. Well, guys, why can't I just cancel the x squared? Doesn't that work?
They're not multiple, they're added.
Good, they're add-ins. This is all being added down here, so I can't just drop them off. That is the common mistake, though. So, if you can't have a GCF, you continue on. The next step is factor what remains. So, look at the numerator. Somebody give me the factors of the numerator, please.
X plus. I need a calculator, please. All right.
X plus 4, X plus 3. Very good, Leslie. Absolutely right. Denominator.
X
X minus 3, X plus 1.
X minus 3.
X plus 1.
No. X plus 1.
X minus 1. Oh.
Be careful, people. Let's go through this, because clearly we're still a little bit confused here. This is constantly, coming up to scare people.
Are you sure?
How do I get this 12 here, and how do I get this 7 here? What are they the result of?
Multiply.
And?
Add up.
Very good. Again, the product and the sum. So take a look. 4 times 3 gives me 12. 4 plus 3 gives me the 7 in the middle. Now, in the denominator, it's a little more tricky. Here's what I want you to notice, guys. If I have to tell you to stop, to focus, come on. The denominator here is a little bit trickier simply because of the negative sign. And pick up on the patterns, people. Whenever there's a negative sign for this last value here, you're going to have a plus and you're going to have a minus. Again, whenever there's a negative sign, one will be plus, one will be minus. It always works that way. Whenever there's a positive sign, like in the 12 up here, either you're going to have a plus plus or a minus minus, but they have to be the same. So if you haven't picked up on that pattern by now, notice that when C is positive, these are the same sign, both positive or both negative. When C is negative, they're alternating. Can't stand the heat, don't eat it.
Get out.
You okay? No, I'm good. Alvin after class, for sure.
What is that?
You see me pretty back in class.
Not now, stop.
Okay.
Now, looking at this problem, we can see already that clearly what's going to cancel here?
X plus 3.
X plus 3 cancels, very good. What's left over when I cancel things? What do you always have behind? Good. You got the 1s left behind. Now, why can't I just cancel those x's? I see an x at top and bottom. Good. They're adding and subtracting, thus they are add-ins. They're not factors anymore. Okay, again, it's very key to note that, please. These two things cannot be canceled. These x's here cannot be canceled. Good?
This is all we have to do.
Well, we're going to do one more example, but this is the general idea.
Oh, I got this. All right.
Remember your steps. What's your first step?
Factor.
Factor.
Good. Factor the GCF, then factor what remains. If you don't factor out a GCF, it ain't going to work here. Okay?
It won't work.
I got it.
So that's how you talk now.
I need a calculator. X minus 1?
Yeah.
By what?
Notice your GCF for the top and bottom will be different. Your GCF for each of them will
This
be
is right.
different.
This is right. I think it's right.
Right. I'm trying to find a calculator.
Be careful, there's no x in 36.
Yeah,
So you can't take out a 4x. There's no x in 12 here, right? So you can't take out those x's you're trying to take out. So you can only take out the numerical value. The rest is right. You can go back and change your fractions and stuff now. Everybody in the top, what's the GCF in the top? 4. Okay, everybody notice 4 goes into 4 and 4 goes into 36. So when you go up top, start with a 4, please. Now, down below, what's the GCF?
2.
How do you know it's 2? Why isn't it 6? 6 goes into 12.
Not 2 and 2.
Good. Doesn't go into 2. It's got to go into everything. So when you factor out a 2 now, okay, drop off the 2's in the first ones and make that a minus 6. This becomes x squared minus 9. Again, in case you're forgetting how to do this, remember, take each of these and divide them by 2 in your mind. Take each of these and divide them by 4 in your mind.
So when can you add the x's like you did on that? Oh, never mind.
You okay?
Yeah.
Now, I still see that I still can't cancel stuff, right?
Yeah.
It looks like I have major factors. So for example, 4 is a factor because it's being multiplied. 2 is a factor because it's being multiplied. But x squared is not a factor. X squared is still an addend. This entire term is a factor. This entire term itself is a factor. But the x squareds themselves are not factors. They are addends. That's why we can't cancel the x squareds yet. Okay? So what should we do to the factors that we have?
Factor.
Factor them further. Very good. What is 4 over 2 though? So we can just cancel this right now. Good. 2 over 1. So please replace that before we go to the next line. Now, remember this was really 2 over 1. I don't need the 1 down there. I'm putting it there as a placeholder right now. Again, you don't need the 1 on the bottom.
So x minus 3, x plus 3.
Very good, Andy. And you noticed up top that x plus 3 and x minus 3 works. Because negative 3 and 3 adds up to the 0 in the middle that it's missing. And negative 3 times 3 gives you the negative 9 at the end. Remember, there's no middle value, so the sum of these numbers must be 0. We'll discuss that in 2 seconds. Hold on. In the bottom, what do you got?
2 and 3.
2 and 3? Which is which?
X plus 2.
And x minus 3? I agree. The reason I agree, again, is because negative 3 plus 2 gives you the negative 1 in the middle. Negative 3 times 2 gives you the negative 6 at the end. Now cancel, please. Cancel, cancel. Your final answer. Now, take a look at this. Your final answer is in factored form, and that's fine. There's no problem with that whatsoever. Okay, you can leave it like that. You could also write it as 2x plus 6 over x plus 2. There's no difference at this point. Okay, traditionally, though, you leave it in factored form. Now, one thing I want to note is this, and Andy already started playing it out. He noticed this x squared minus 9. This is a very exceptional case of factoring. Does anybody know what this case is called? Algebra 1 term. What is it called when you always have something that looks like the numerator, x squared minus 9, and you get x plus 3 and x minus 3? What is that called? There was a special name for it. It's an acronym, so it starts with a D. It's an acronym. Dots? Do you remember dots? Okay, let me explain this then. Let's go ahead and write this. This is an example of dots. Now, it's no big deal if you didn't learn it now. Dots means the following.
Division, definition, difference of two squares. Okay.
Okay? Difference of two squares.
Looks funner.
Difference of two squares. Now, relax guys, focus. When you do this kind of a problem, it gets very complicated. Okay? And a lot of students get really confused on the SAT, and these problems are on there all the time. It's one of the biggest factoring ones. So I want to spend some time going through this now. So for this example, we were able to see that it was, yes, x plus 3 and x minus 3. Now, there's a way we can generalize to make this easier on us. So no matter what we have, we can always do this. So let's take a look. We have x squared minus 36. What would that become?
X plus 6, x minus 6.
X plus 6, x minus 6. Again, we take a look right away. What is the pattern that you're noticing here between these two examples? Negative and positive, very good. One has to be negative, one has to be positive, so they cancel. So this number here, Leslie, this 6 and this 6 is the what of 36?
The square root.
The square root. The square root. You're right. Once you multiply 6 and 6, you get 36. 3 by 3 give us 9. But this number here always becomes the square root of whatever's over here. Even here, same thing. What's the square root of x squared? This is x. That's what this is right here. That's what this is right here. So we can generalize this. And what I mean is we can write a statement for all counts. So what if we have something like 4x squared minus 25? This is dot still, because this is a perfect square and this is a perfect square. And what's the other one? Again, take a look, please. What's the square root of 25? Isn't it just 5? And that appears in two spots. This 25, its square root appears there and there. Well, what's the square root of 4x squared? It's 2x by 2x. So no matter what, if you have a perfect square in these two locations, you can always use this technique, assuming it's a difference. That's why it's called difference of two squares. This sign must be negative. Notice, it's negative in every case. If it's a positive, it doesn't work this way. Again, it does not work this way. If it's a positive, you get imaginary roots, actually. That's what that comes about. Let's look at a more complicated example. What if we have...
Could you have like 4x squared plus 25?
Is that y? Minus?
That's a y.
Don't go on my watch.
9 over 49 y squared minus 81 w squared. What do we got for this one? Same rule applies, people. Same rule applies.
9.
Can I get one hand, please? I know a lot of you might have the answer. Andy?
The 81 part is 9w.
Good. The 81 w squared becomes 9w. That's clear, right?
Yeah.
Just like last time, the 4x squared. So again, we're splitting up into two terms.
Oh.
We definitely have a plus 9w
And with that one,
and a minus 9w.
3 over 7y.
Very good, Andy. What's the square root of this? Again, the square root of 9 becomes this 3. The square root of 49 becomes the 7. The square root of y squared becomes the y in the front. So this becomes 3 over 7y. Again, because I know this is a little bit messy here as you see it. You have 3 over 7y minus 9w, 3 over 7y plus 9w. And I know this sounds kind of weird and this looks kind of weird, but these are the kind of problems that you're going to have to use on the SAT, or these techniques. Okay, if you're keeping up with the online SAT course, you're going to see that this week, actually this week's recording, which will take place today, I'm going to post it, you're going to see that this actually is one of the topics covered, factor. Okay? So again, break it up into its components, please. Break it into its components. You're not going to see much more complex than that. I did another example in the honors class that maybe I'll go through real quick with you guys. What if you have something like this now? This is where it got really confusing. What if you have... What about this now? This is a tough problem here.
7. 7x squared.
7x squared. Why is it x squared? Again.
Square root of the x to the fourth.
Very good. Take a look here. X squared times x squared is what gives you x to the fourth. That's why it's x squared.
Minus 6 to the 3rd.
Minus 6x to the third plus 6x to the third. X to the third times x to the third is x to the sixth. So what do you notice about this? When you take the square root of anything with a exponent. When you take a square root of anything with an exponent, what can you do just to start off the bat?
Negative and positive. I don't know.
If any exponent divided by 2.
Good, Kelly. Very good. There's your rule. So take a look. Again, we'll talk more about this later. But here, if you took this exponent and divided by 2, that's where the 2's came from, really. Take the 6 divided by 2 and you take the square root. That's where the 3 really comes from. So we're going to see later on that if you take the square root of anything, if you take the square root of x to the 10th, it just becomes x to the 5th. If you take the square root of x to the 20th, it becomes x to the 10th. It's always half of it. Okay?
Can you put,
So for these kind of problems, I know they're complicated, but it's good to know.
Can you put 6x to the 4th and then 6x to the 2nd? To mess around.
Can you put what?
6x to the 4th and then 6x squared.
No, because even though they add up, they're not going to cancel. If you factor the back out, they wouldn't cancel out. Okay? One last one. What if you had this now? What if you have x to the 4th minus 1?
X to the 4th minus 1.
X squared. X squared
plus 1.
Very good, okay. Are we done though?
Yeah.
No, you,
What can continue to be factored?
the x. I mean.
The 1.
X squared.
Yeah, the x squared, that x.
Oh yeah, it does go to
X.
x. X minus 1, x plus 1, x.
Good. This one can be broken into two other factors. Very good, guys. Again, x plus 1, x minus 1 over here. So in the end, your actual factors, you have 3 distinct factors here. Not only just these 2, because this one can be broken further. So keep that in mind as you're doing these kinds of problems, okay? Just because you break it down once doesn't mean you can't do it one more time. Questions on this? No. Hey, tonight, your homework is to do one side of a worksheet. Okay, the front side here. What I will do is tomorrow we're going to start the next concept, but I might give you some more practice ones. You don't need to work on the back ones. If you want to try the back ones, you can. But the back ones, you have to use AC method to factor. Okay, which was from a while ago. AC method is not really on the SAT actually, though. So I'm not going to go into crazy detail. Okay, even though I put some problems in here that have it, just so you know. Okay, on the back, some of these have AC method. So you're just going to do the front for tonight. 6 problems of practice. Okay, tomorrow we'll have our first attempt or our first practice quiz on this.